you hear me well, right? So just type it in the chat or let me know if there is any problem. So welcome everyone. This is a new course titled Introduction to Fluid Mechanics. Okay, and yeah, so this is a course that I'm going to teach together with Gloria here. Eduardo García Juárez. Myself, Javi Gómez Serrano, and Jamil Paz. Is the handwriting good in terms of size? I mean, in terms of quality, probably not so good, but let's talk about that later. If you want me to write bigger, let me know, especially the people on Zoom. And you see all the way up to here, right? This is for the people on Zoom. You can see up to here, just to get an idea of how I can write. Okay, wonderful. So going to meet Monday and Wednesday from noon to 1:30. Whoever is in person, which is going to be in the room that we are here, at T1 at UB, and on Zoom. And moreover, the lectures are going to be recorded. Okay, some more details on that soon. Okay. For announcements, there may be some announcements, like, I don't know, change of room, or say, canceling classes, or change of topics. There will be a mailing list. And for that, I will use the emails from the people who register. So whoever has not registered, please register, because this is the thing that I'm going to use for communication with the class. Okay. So most of the people have already registered, but especially if you got the Zoom link somehow, make sure that you are registered, because otherwise, I don't know, maybe a class canceling and you come here and there is nobody here. So that's bad. Okay, so this is the class, and the main plan is the following. So this is going to last 15 weeks, approximately. So more like the whole semester. I'm going to be very slow, painfully slow. Okay, so for the specialists, maybe too slow. But again, this is targeted to non-specialists. However, if you're a specialist, don't despair. So there will be maybe a few lectures, and I insist on the few more technical. Okay, so I try to find some balance, and the level is quite heterogeneous, so I'm trying to please everyone, and I don't want to lose anybody. So my point here is I will keep a slow pace, and you'll tell me what is slow, because you will have a say on how fast or how slow I go. By default, if I don't hear complaints, that means I'm going too slow. So I may go quicker. But I'm happy to slow down. And yeah, I don't want to bore the specialists either. So maybe some lectures may be more technical, or I don't know, more targeted towards them, involving new stuff. So those may be more suitable for them. Okay. This is pretty much what we are going to talk about. So this is the plan, and well, this is the plan for today. Let's see, maybe this can change because the course is very long. So we're going to start with some introduction to Euler and Navier-Stokes. Okay, and will be the one delivered in this class. Then we're going to work on bifurcation theory in a broad sense. And this will be Claudia. And at the very end, Camille. We will also talk about rigidity and flexibility. In the context of fluid mechanics. Then there is going to be a part on weak solutions, Businesque, and inhomogeneous Navier-Stokes. And the last part is going to be on numerics, computation, this is going to be me again. Okay. So roughly, this is going to be 1 week, 5 weeks, 3, 4. Also, this is very, very tentative, and we'll adjust. But just to give you a feeling of how the course is going to be structured and how the lectures are going to be organized. These are independent blocks. Okay, so independent blocks. If you know everything about one of them, or if you don't want to know anything about it, you can wait for, I don't know, you'll see. I'll send an announcement when we change flow. Okay? So it should be self-contained. I mean, of course, if we talk about Navier-Stokes, you will be supposed to know what the Navier-Stokes equations are, but not more. Okay? So within reasonable constraints, every block is going to be independent from the rest, more or less. Okay, and there will be also some connections. I know there are not many people doing fluid mechanics, so especially for grad students, this is going to be connected with elliptic PDE, and this is going to be connected to parabolic PDE. So even though you haven't seen anything on fluids, this is fine because there will be some connection to more like elliptic PDE, calculus of variations, or parabolic PDE. Okay, and maybe here we can say dispersive PDE. Yeah. There will be some surprise lectures. Meaning, I'm not going to lecture on a Wednesday at 7 p.m., but that the topic may change. Okay, so there may be some, and this is connected with this. Okay, so there may be, depending on how we're doing on time, some talks or some lectures on new stuff. A new means really new. So new means that it will appear on archive that week or something like that. Okay, so really the latest of the latest. But we'll see, depending on how we do on time, and depending on how we do on the papers, we'll see what we cover. Any questions so far? Any comments? No exam. The class will be cut. You will all get an A. Okay, so no. This is the typical question that I would hear. No homework. Okay. I won't take assistance into account. You don't have to kill your grandmother to justify that you're not here. Okay, so some references. Also, if I write too quick on the board, let me know as well. Yeah, so for the most part of for one, I will be following the book by Maida and Bertocci on vorticity and incompressible flow. Which is the first book that I brought today. I mean, it's big. It's big. But it's a good book. It's quite comprehensive. Yeah, exactly. Exactly. Maybe not happy, but okay. So yeah, the book is quite good. It's comprehensive. There are some typos, especially concerning sign mistakes, but otherwise the material, the treatment is good, especially for a beginner. Parts of it will also be used in chapter 4 as well. So for 2, we will use the book by Hilhofer, bifurcation theory. And Buffoni and Cohen analytic theory of global bifurcation. And for the last part, some lecture notes by Verti. Lecture. Okay. For 3, this is a classical text by Lee and Laws analysis, all related to symmetrization, calculus of variations, etc. And for 4, there is the additional reference by Robinson, Rodrigo, and Sadowski. This is the new book called the 3 Navier-Stokes. And for 5, I will use lecture notes written in form of a paper. Published at the semi-book. Okay. Yeah, so this is the plan. Everything you can find it online with more or less effort, more or less help, more or less free. You know what I'm talking about. So yeah, if you can find any of these or some of these, just let me know and we'll figure out a way. Okay, so that's pretty much like the basic bibliography, and this is mostly where we will be taking the material from. We will also use our own papers in parts of the class, but this is more or less the plan. So far, so good. Good. So now it's 20 minutes past. Let's start with the real class. So I'm going to talk about the Euler and Navier-Stokes. So I won't spend too much, or I won't spend barely any time at all in the physics, and I will just concentrate on the mathematical part. I mean, I will give some physical intuition about how things happen or why things happen, but in general, I won't spend a lot of time insisting on the physics of everything. Okay, so let me start by presenting both the Euler and Navier-Stokes equations. So incompressible flows, let's say of homogeneous fluids for now. So I'm going to assume constant density in the whole fluids. Incompressible velocities, incompressible flows. So these are solutions of the following equations. V dt is equal to minus grad T plus nu delta V. I want to add some forcing here, but in general, I will usually take this to be 6. Okay. This is basically Newton's law. So this is m dot A, and I'm dimensionalizing everything to be 1, and these are the forces. So viscosity and the pressure, and maybe some external forcing. We could put gravity, for example, if we were looking on the space or something like that. But for now, let's neglect F. This is basically second Newton's law. The velocity is divergence free, as I said, and there is some initial condition, which is given by some initial condition V0. Okay, so this is more forcing. V is the velocity. Usually, our domain, I didn't say much. I mean, I didn't say anything about it. I'm going to take V, living in either Rn or Tn. I could do this in a finite domain, but I won't do it. So for simplicity, let's take our space to be either the whole space or a periodic set, either in 2 or in 3 directions. P is the pressure, and nu is the viscosity, which I'm going to take as a constant, independent of everything, independent of time, independent of space. And d by dt, the capital D, is going to be the material derivative. So partial T plus V. I want to write this in coordinates. This is going to be partial T plus the sum of VI. I may not write sometimes the sum and use the Einstein convention, just in case if you see the signs disappear, this is what is happening. Okay. Good. So this is our enemy, and this is what we are going to be looking at for some time. And of course, in there are 2 or 3, which are the physically interesting cases. Good. So if u is equal to 0, then 1 becomes the Euler equation, the incompressible Euler equation. And if nu is positive, then this becomes the incompressible Navier-Stokes. So this equation is from 1755, and the second one is well, 1841 Navier and 1845. Okay, so pretty old anyway. In fact, the Euler equation is the second PDE ever written at all after the wave equation. Okay, so if we look at this, then okay, this is I wrote it in a compact way, but this is actually a system of equations. If I consider this and this, then equation 1 are n+1 equations and n+1 unknowns. So V1, Vn, P. Okay. So the system, in terms of that, it looks good, it looks balanced, and we have as many constraints, as many equations as unknowns. So that's good. That's good. And yeah, so after having written up the equation, the main question here is the following. And I'm sort of simplifying a little bit because I don't want to talk about the forcing. So there are two possibilities. Either systems and smoothness of solution for all time, assuming that the initial data is good enough. Assuming V naught is smooth enough. And some decay conditions if we are in the case of Allen. For all okay, so in other words, if no matter what I put here, assuming some regularity hypothesis, will I have a solution for all time? Okay, so if I start good, am I going to be good forever? This is sort of another way of recast this question. And okay, so that's one possibility. And the other possibility is, can I find a V naught, which is nice, such that the corresponding V, which is the solution of this initial value problem, blows up. Okay, so in other words, when I say it blows up, I mean that V becomes infinite. Okay, so these are basically the two alternatives. I'm going to leave the equation there. So that was the question, and now the answer, or some answer. If n is 2, then A holds. Even if nu is 0, which is harder in that direction. So if we are in 2D, then if we start regular, we will be regular forever. Even in the case where there is no viscosity. The viscosity helps to be regular because it smooths out everything. It makes the solution to be smoother. So even if we don't have viscosity, which would help if we were trying to prove A, life is good. So this was proved by Senskaya. Oh, I made a mistake. So, in the 60s. Okay, that's good. And if n is 3, then this is the Clay price. If nu is not 0. Okay, if nu is 0, then it doesn't come with $1 million, but still it's a good problem. It's a 250-year-old problem, so it's maybe worth thinking about it. Okay, so this is the main question. We're not going to solve this question today. But we are going to try to at least understand why this is a hard problem. Okay, so throughout this class, we're going to use two points of view. Okay. We may talk about the equations and the evolution equations from the Eulerian point of view. Okay, what do I mean by the Eulerian point of view, or the Eulerian framework, or the Eulerian coordinates, is the following. So I'm going to ask, what is the value of a quantity at some point in space-time x0, t0. So what I'm doing here is, okay, I'm looking at the fluid, I'm looking at whatever quantity I'm looking at, and I'm taking a picture. So at time t0, I say, well, what is the velocity at my point x0? Okay, and then I will know. So then this gives me a number. So this is similar as taking freezing time and taking a picture. Or, I mean, one can interpret it also as the following. I fix my favorite location in space, and I say, well, what is the value of the velocity at that particular point in space as I move a long time? Okay, that is the Eulerian framework. Now, in contrast, Then is the Lagrangian framework, which essentially what it does is the following. So I touch a particle. Okay, so I look at my fluid at some time, let's say time 0, and I pick one particle. And I say, okay, this one I color it in red, for example, and then I'm going to see what is the evolution of that particle. Where does it go? How does the velocity of that particle evolve? And then particle. Okay, so this is pretty much what you see sometimes in experiments. If you watch videos where they use dye to color, like they have some, I don't know, some fluid or some viscous fluid like glycerin or something that doesn't have a color, and then they put dye, and then they do nasty things to the fluid, and then you can see what is happening to the dye particle. Okay, so this is more like, okay, I select something and I see where does it go, how does it move, and so on. So I were to draw a picture, the Eulerian point of view, we say, well, I take a photo and I see how does it look like, and then I take another photo and I see how does it look like, and so on. Whereas if I were to look at this in Lagrangian, then I would have like a space-time slice where my particles are. My fluid, I fix one, and then I move to the next time slice, and okay, this wanders around, and it gets here. Okay, so I'm just looking at this particular instance or this particular particle, and I see how does it move throughout the fluid. Okay. So these are going to be 2 points of view, 2 different points of view, and each of them has advantages and disadvantages. And we're going to try to use all of them to our advantage. Okay? Any questions so far? Any comments? I'm going too fast? Too slow? So? Okay, good. Okay. So this equation has some symmetries, and this may become important later on. So if we have a solution B and P, which is let's say either Euler and or Navier-Stokes, then if I take translations, see semi-arbitrary vector in Rn, or rotations, or Q is a rotation matrix. Or dilations, depending on now 2 scales. If we are looking at Euler, so lambda over tau V of x over lambda, V over tau, lambda square, tau square, V x over lambda, V over tau. Okay, so in Euler we will have 2 degrees of freedom, 2 parameters, 2 scaling parameters, and for Navier-Stokes we will have only 1, which I'm going to call it tau. Then 1, 2, and 3 E are solutions Euler. 1, 2, 3 NS. are solutions of that. Okay. This is very easy to check. I won't check. Okay, so now let's move to Lagrangians and let's study some properties of the mapping that tells me that if I'm here, I mean of the flow map. So that tells me that if I'm here at time 0, then where am I going to be at time 1? And so on. Okay, so I'm going to explore, prove some of the properties of this flow. Okay? So this is called the particle trajectory mapping. So I'm going to call x of alpha t the Lagrangian map. So I'm going to, what do I mean by the Lagrangian map? I mean the flow map at time 0, I'm the identity. Right? So essentially, this is the flow map of the PV. So if I start at time 0 at the point alpha, so I'm fixing this marker here. Where am I going to be at time t? Okay, this is, yes.
I complain about the x.
Well, you're going to see lots of x's. This is not going to change. I take complaints, but this. But okay, I'm going to write it like this, so that there are no confusions with the coding. Okay, so then x solves the following: d by dt x of alpha t is simply v of x of alpha t, and the initial conditions x of alpha 0 is equal to 1. Okay, so why? The natural interpretation is that if I fix a time slice, then the velocity, say if I were to fix something here, then the velocity is going to be at this time slice, at this point, is going to be tangent to the trajectory. So the interpretation, and this is where this is done. That the tangent vector of the trajectory then, and this is how we get it. Okay, so now I'm going to study some properties of this flow. So, first of all, find J as the Jacobian of gravitas. So, I mean, now the letter is chosen for a particular reason. This is coming from the Jacobian. And this is useful, for example, so this is a very natural object that is going to appear whenever we are trying to go from Eulerian to Lagrange. because we're going to try to swap coordinates, and then this is a natural object that will appear when changing, for example, the dx into the d alpha inside inside of an integer. Useful when changing variables from Eulerian to Lagrangian and okay. Good. Yeah, I think by this point we know what is Navier-Stokes. For competition 1, let's try to compute the evolution of J in time. So J partial to J is equal to the divergence of V at the point dt times J. Okay. So this is the PDE that my change of variables is going to satisfy. Sorry? No, not well in general. This is in general, without assuming anything. Later I will find a characterization of incompressibility in terms of this. Okay, so this is in general, without, there is no PDE, there is no Navier-Stokes here. This is just for a fluid that is being transported with a velocity. But yeah, I agree, for most of the lectures, this will be constant in time. Okay, so let's prove it. So this is a linear algebra exercise. So somebody is looking for us. Somebody is teaching linear algebra and looking for a problem. This may be a good problem. Okay, so let's compute slowly using the definition. Okay, so dtj is simply dt, the determinant of the Jacobian. Maybe let's write this down differently. The determinant of the matrix D xi, D alpha j. Okay, here I haven't done anything. And okay, so far so good. But now I do it with the function of the determinant. So now this is equal to the sum in Ij of the Aij, which I will explain what they are, dt, dxi, d alpha j, where the capital A's are the minors of dxi, d alpha j in the depot. Is this clear? Why this is true? Yes? Oh, good. Okay. Linear algebra is pretty good. I have to sit down and think about it for a little. If you take the multilinear expansion and expand the derivative, put it in all the terms, in all the products, this is what you get. Okay, good. Now, this is nice because we could take a derivative in x here and we would be able to write this guy. So that's good, and this will come in terms of V. So now, what else can we do? Okay, we're going to use the following identity, which is also Okay, maybe not easy, but one can do this. And again, this is multilinear expansions. Dx k d alpha j a ij is delta ik j. This is the Kronecker delta. So delta ik is 1 if I is equal to k and 0 okay, so this is also a linear algebra identity, reasonably easy to establish. Okay, so now I'm going to use this, and I'm going to take the derivative here, and I'm going to use, I mean, that's partial d, everything is smooth, I'm not going to worry too much about that. So this is the same as if I keep this equation here with a partial alpha j. So what am I going to get? So dtj is equal to the sum in I and j, and now the sum in k, aij, the gradient of vi times dxk d alpha j. Okay, this is, I'm not doing anything, it's just a chain rule. So I'm differentiating that equation over there with respect to alpha j. So I have to keep with dk here and then use the chains. Okay, and now I use the identity and I sum in j. Now this is the sum in I and k of dk di delta ik j. And now I substitute for the definition of the Kronecker delta. Now I get that I has to be equal to k. So that this becomes the sum of dk dk j, which is the derivative of b times j. Okay. So this is evolution of the change of values, or of the volume form of the flow. Proposition 2. I'm going to talk about the transport formula. And this is going to be later useful whenever we are trying to compute time evolution of quantities, always working in Lagrangian problem. Okay, so suppose that I have a domain, which I'm going to presume it's nice. So open, bounded, and smooth, and when we take x, the particle trajectory map before v on the for every f is smooth d by dt of the integral of f over my domain x of omega t. The integral over x of f sub t plus the divergence of f d dx. Okay. So this is what is usually known as a transport formula, and the problem, like if we want to do this blindly, then the problem is, well, prove that everything commutes with everything. This is not an issue. So if I take the derivative here, if I keep the f, good, I'm going to get an f sub t, but the problem is how to quantify whenever this derivative hits here. Right, so this is difficult. This is annoying So we're going to fix the external domain and then take the derivative of whatever we get. And whatever we get is going to involve the J. Okay, so let's prove it. So we change variables. And okay, so the integral over here. Okay. Now I take little x to be big X of alpha t, and I have to integrate over omega f of big X of alpha t j alpha t dx. Okay, so now, as I said, this is nice because it's a fixed domain of integration. And then there is no problem, assuming everything is smooth enough, on taking derivatives and moving the derivatives inside the integrand, as opposed to dealing with the annoying part that the domain of integration is time dependent. Okay, so now, using this trick, then we take the derivative. Now we see already that it is important, or it comes in the proof, the derivative in time of the J. So if I now substitute and use the previous lemma, then this becomes the integral over omega, partial f, partial t, plus grad f, partial x, partial t. Okay. This is when the time derivative hits the first one, plus f jt. And now we're going to use the previous lemma. One, or proposition one. This is of x plus, now jt was the divergence of v times j. So we have f, divergence of v, everything times j. Okay. And now this looks good. I have a j. I can move back and change the j d alpha into a dx. So now I do exactly that, and I put these two things together as part of a common divergence. So now I have partial f t plus the divergence of f v and v. This is everything. Okay. So this is exactly what we wanted to do. Okay. So now I'm going to say that the flow x t is incompressible if for every domain, let's say smooth, and for every positive time, the volume of x of omega t is equal to the volume of omega. Okay. Namely, if I take my favorite region, I evolve it with the flow, the volume of that region is not going to change in time for any time and for any region. So this is how we define an incompressible velocity, an incompressible vector field, or an incompressible flow. Okay, so with this definition, corollary of the previous two propositions. Take f is equal to 1 in this lemma. This is precisely the volume without the time derivative, and therefore that thing has to be 0. So if f is equal to 1, then the time derivative of the volume is equal to the integral of the divergence v dx. Now, this holds for all t and for all omega. Therefore, this has to be 0. I mean, this is 0. If incompressible, then this is 0, which implies for all t omega, which implies the divergence of v. And moreover, if the divergence of v is 0, then this is coming back to your question, then j is constant. And j of alpha t is j of 0 t, sorry, j of alpha 0, which was the identity. Sorry, x was the identity, therefore j is 1. Okay, this is from evolution. So, an important quantity or an important function, and I will speak more of this next day, is the vorticity. Okay, so this is an important function, and this is an important physical quantity that we are going to study, and this is something that we are going to pay attention to. Okay, so omega is by definition the term of v. Okay, so okay, you can complain, but yeah, what happens if v? I mean, this only makes sense if v is a vector in R3. What happens in R2? Well, in R2, I'm going to take omega to be a scalar. And in 3D, this is a vector. Okay, so pretend that omega in 2D was omega 1, omega 2, 0, take the curve, and then what you get in the z direction is going to be my scalar. Okay, so if v is v1, v2 in 2D, v1, v2, extend it to R3 by considering v1, v2, 0, take the curve, and then you're going to get something that it only lives in the z direction, and this is going to be my omega, or my understanding of omega in 2D. Okay, is this clear? The convention. Good. So omega roughly is going to measure how much the fluid rotates infinitesimally, but let's say yeah, and this is going to be important later. I just want to define it today, but we will play with omega some other day, Wednesday. And later on. I mean, omega is going to appear many times. Okay. So, yeah, let me sort of try to give some idea of what things may be going on by explaining some simple solutions. So I'm going to construct some particular solutions that are sort of very dummy in some sense, and the movement is very controlled, but just to explain how rich the equations are and the type of things that could potentially happen. Okay, so first solution that I want to talk about is the jet. And you will see in a minute why this is called the jet. So let me take some numbers, gamma 1, gamma 2, positive, and let me consider B given by minus gamma 1 x1 minus gamma 2 x2 and gamma 1 plus gamma 2 x2. And P minus a half gamma 1 square x1 square plus gamma 2 square x2 square plus gamma 1 plus gamma 2 square. Okay, so I claim that this is a solution. And if you substitute, unless I made a mistake, it should be a solution. Yeah, I mean, maybe there is a 2 hidden here or there, but this should work. Yeah. Well, it doesn't matter because if you take the Laplacian of this is zero. Okay, so okay, this looks like magic, but let me sort of analyze this system a little better from the point of view of the Lagrangian formulation. Okay, so let's write down the particle trajectories. So now this is sort of explicit and good. And if I try to compute the evolution of x, this is going to be given by minus gamma 1 x1 minus gamma 2 x2 and gamma 1 plus gamma 2 3. x1, x2, x3 are the different components of x. X is a vector. And then denoting x super 1, super 2, super 3 as the 3 different components of x. Now this is a simple ODE. This one I know how to solve. And of course with condition, how to say this equal to alpha. So what I get here is an exponential. Depending on the sign of the gammas, it's going to be growing or increasing or decreasing. Okay, so this is E minus gamma 1 t, E minus t, E gamma 1 t. Okay, so what's happening here? Suppose that we take a particle somewhere here. Now, in the x1 and the x2 direction, this is okay. This is x1, 2. Okay. In the x1 and the x2 direction, this is exponentially, and let's draw the axis. This is exponentially decaying to 0. Now, in the x3 direction, this is exponentially growing to either plus infinity or minus infinity, depending on alpha. So for this alpha, it's positive, and therefore it will go to plus infinity. So essentially, this is just going like this. If I were to start somewhere here, it would do something like this, and so on. And similarly, in the case where I start below the x1, x2 plane. Okay, so now you can see why this example is called a jet, because essentially this is sort of going up or going down, and that's it. That's sort of the movement of this type of solutions. So this is what they do. Now, if you look at this, the solutions are kind of being sucked either from a sink at plus infinity or minus infinity, and then towards the axis, right? So this is essentially a sort of like vacuuming the particles. So there is no chance that a singularity is going to happen here. Okay, so something important is that there is no swirl or no rotation. This later will imply no singularities. So if we are looking for a candidate that produces a finite time singularity, let's say for Euler, and we are optimistic, then it cannot be like this. Okay? Something else has to happen. This is too rigid. It will just go up exponentially fast, but nothing will actually happen. Okay? The particles are not going to collide, for example, or they won't hit each other in any way. Things will not go bad. So this is okay. It's a simple candidate, but we're sort of trying to understand like the basic moves of this equation. So let me talk now about something radically different, which is a vortex. Okay, so these are other types of solutions, and I'm going to set V minus a half omega naught. Omega naught is a number, x2, 1/2 omega naught x1, 0, and T is minus a quarter omega naught square x1 x2. Okay, so if I take these two ansatz, then that's also a solution. I mean, here I'm keeping alone because none of these things has finite energy. So pretend that we're overlooking that as well. None of these things decay at infinity, for example, but pretend that these examples are understood in a local sense. So I'm sort of thinking about what may happen towards, let's say, here or here, something like that, and imagine that I can deal with infinity in some other way. Okay, so let's not get into that discussion yet, but just as a disclaimer, none of these things has finite energy, so it wouldn't really qualify towards saying something about the singularity per se, but we are trying to understand this as more of a local behavior around certain points in our fluid. Okay, so if we look at that and we write down again the particle trajectories, the ODE for the trajectories, then we get also something nice. Okay, so this is our evolution equation for the Lagrangian map. This one is easy. So this implies that x3 is alpha 3. And this one, it's also easy. This is alpha 3. Okay, so if we solve this bit, then we can easily obtain x12 alpha t with some rotation matrix with frequency 1/2 omega t alpha 1. Okay, and q is the rotation matrix cos minus okay, so again, a very simple behavior, a very easy movement, easy to describe, easy to solve, but of course, no finite singularities. So essentially, what is happening? This is the x1, x2 plane. Here the movement is 2D, and pretty much things are going around in circles and nothing really happens. So the particles rotate around, fluid rotates, but that's it. So nothing exciting happens. So pure rotation, no singularity, which is bad. Okay. So let's try to twist our example and try to combine this one with that one. So let's try to see if we can put some movement, some rotation in this trajectory, and see if we can maybe find something that that does something slightly different, more complicated, in a way that perhaps the particles could potentially collide with each other. So the idea is to combine the vortex and the jet. Okay. In order to produce finite singularity. The spoiler we won't be able to do, but let's see how the example looks like. So let's look at the rotating jet. Okay, so now I'm going to pick B, something more complicated, gamma 1 x1 and 1/2 omega t x2, 1/2 omega t x1, gamma 2 x2, and here gamma 1 plus gamma 2. And omega of t, omega of e to gamma 1. Okay. So now we're putting some rotation plus the exponentially growing or the exponentially decaying modes that we put in the jet. Okay. And the pressure, I'll leave it as an exercise. Not too hard. But you can believe that there is a pressure for which this makes sense, and it's a solution of Euler and Navier-Stokes. Okay, now let's do the analysis of this. So, well, the first component is trivial because this is just a pure exponential. So x3 is e to the gamma 1 plus gamma 2t alpha 3. Here I didn't really do anything at all. And partial t x is, if I write it in matrix form, gamma 1 minus gamma 2 minus 1/2 omega, 1/2 omega. And if we solve this, then we get precisely what we were expecting. There is some component accounting for the exponential behavior and some component accounting for the rotation. Everything is linear. We could decouple the system and see that this piece accounts for the rotation and this piece accounts for the translation, for the exponentially growing or decaying. So basically, if we take a particle, let's say here, then it's going to sort of do something like this. Okay, so bear with me, do an exercise in imagination, and pretend that this is a spiral sort of going down, going around like this, and getting to the axis exponentially fast, and getting to infinity exponentially fast as well. And similarly on the other side. Okay. So this again doesn't help, but this is sort of the mental picture that instructive. Yes, yeah, towards. But instructive in that sense. Yeah, but here I could imagine a singularity forming because of two particles colliding, for example. So if two particles collide, then something has to become bad, something has to become infinity. Okay, the flow map is not going to be bijected, this sort of thing. So then if something like that happens, then one could track exactly what happens and maybe orchestrate it in terms of the velocity or something like that. But certainly some regularity is going to be breaking down. Okay, so this is that, but, and I will finish here with this. So, I mean, why do I insist so much on these things? If we were to look in nature, a singularity, let's say, okay, assume that the world is ideal, a singularity is like a tornado. So when a tornado is forming, pretty much the air is rotating faster and faster, and at the tip of the tornado, a singularity is forming. I mean, something is blowing up there, or it's very high, right? So from nature, one of the examples that we could think of would be something along those lines physically. Okay, so yeah, just to clear this, maybe sometimes. So the air is also a fluid. Whenever I talk about fluids, they don't need to be liquids. They could be air. They could be stars. Okay, so if you think about nature and how these sort of singularities form, and how do they look like, this is a natural candidate, or at least this is some candidate that we do observe in real life. So if the Euler and Navier-Stokes equation model real life, which let's take that for granted, then a possible singularity may look like that. And this is what somehow claims. This is a tornado singularity taken from a paper in the archive of 2021, 2022, and ongoing, where this is an numerical paper. Okay, so, and of course it is not as simple as any of these. But so I encourage you to look at this and as you have already seen, I'm not very good at drawing, but pretty much the way the potential singularity looks like this is the following. So things sort of look like this, spiral along, and they roll around, but in finite time, there is a tornado forming here. So this is the side view. And if I do the top view, then the velocity kind of looks like this. And so on. And it seems that over time, in finite time, things spiral around, and at the tip, which is the center, which is the axis, then finite time go up or blow up of the vorticity occurs in finite time. Okay, so this is a very recent paper. There are follow-ups, and this is new, looks quite exciting, and this is the latest scenario for finite time blow up for 3D object. Okay, and the numerics look quite convincing. So let's stop here, and we continue on Wednesday. But as I said, this is, I mean, there is no theorem here, but the pictures look already pretty good. Okay, so if you want to take a look about how perhaps a finite time singularity for 3D Euler may look like, then go and read that paper. Okay, so we'll stop here, and that's it for today. Any questions or comments from the virtual audience?
Sorry, Javier. One question. Do you listen to me?
Can you again or type it? I hear you, but I don't understand you.
Sorry. Do you listen to me or not?
Sort of. I mean, the volume is good, but the content is a little dark. So it is not a volume problem, but I think it's a little distorted here. I can't understand very well.
No. The question, which is the author of these examples? I cannot read very well. Which is the author of the example?
Thomas Hart.
I cannot see because it's not in on the blackboard. How? Where is he from?
Sorry? Where is he from? He's based in Caltech, but he's me.
Okay. Okay, thank you.
Thank you, Joan. More question? Oh, yes.
Yeah, about the solution with intelligence.
Yes.
So in mechanics, we do blow-ups as well. So
Meaning
the local behavior of the solution.
yes. Yes.
Could it
Yes.
model what's going on?
Yes. That. Yeah. We do that. The terminology is a little different. Like. This in this context, people call it like self-similar solutions or locally self-similar solutions, and it certainly uses the scaling that I wrote down. So yes, the short answer is yes, and there are some results about the existence and non-existence of self-similar solutions of certain types. Okay, so yeah, it's a different name. But from the point of view of the math behind it, it's the same. Yes. Yes. Yeah. You want to put more dissipation or less dissipation? If you put more, then if you put more, then probably there is global existence. There are papers by Camilo de Lelis and other people working with these models. This is called the hypodissipative Navier-Stokes. And probably plenty of other people whose name I forgot. But there is literature when you place the full Laplacian, and instead of having like nu Laplacian, look, if I do like this, you may have something like nu and lambda, some power beta, and then depending whether beta is bigger than 1, smaller than 1, there are things in each direction. So yeah, there is some literature, but off the top of my head, I don't know exactly the results. But yeah, certainly people have tried to put to change the dissipation to see if one could do something along those lines. Okay. No questions? No? Okay, so then let's reconvene next Wednesday at the same time. Hopefully we will start on time then. Okay, see you all. Bye. Close the session.